Well, you have arrived at the most complicated and deepest chapter in this course. And these are IV solutions in which you also must make some drug calculations. And since they're drug calculations, some of them will involve the patient's weight. For example, there's a new unit to be confronted, and so often you will see milligrams. Let me write this out in sentence form. Milligrams per kilogram per minute. Okay, I suppose that could be milligrams per kilograms per hour. It could be grams per kilogram per hour. Anyway, it's a weight of the drug per patient body weight per unit time. You could also have the patient's body surface area in this calculation. And so, but let me just focus on this particular one, milligrams per kilogram per minute. And the way to interpret this unit is milligrams go on top per kilogram per minute. So this is a times. So per kilogram per minute means we're dividing by both kilograms and minutes. In other words, these two units are in the denominator are actually multiplied together. All right, so that's a new type of unit you'll run into. Another new issue is that sometimes you're going to need to first mix the drug into a liquid solution, and that liquid gets poured into the IV bag, and so that's going to increase the volume of the liquid that needs to go to the patient. So you will have to first, in some cases, you'll have to first calculate the amount of the solution being poured into the bag, and then use that total amount of liquid in your final calculation. So that complicates things a bit. All right, so let's get started on some of these. After reading our first problem here, you may want to pause and sort of take it all in, try to figure out where you're going with it before you see me work it. All right, so here it goes. The doctor prescribes 500 milligrams of a drug in 400 milliliters of D5W to be infused in 8 hours. The drop factor is 12 drops equals 1 milliliter. Now that's another way of saying 12 drops per milliliter. The drug label shows a drug concentration of 125 milligrams equals 10 milliliters. What is the flow rate in drops per minute? All right, so what you see here is that we first have to mix up the drug. You know, the prescription, the drug is in solid form, but the drug comes dissolved in a liquid. So we have to tell how much liquid to pour into the IV bags. In other words, we're going to add to the 400 milliliters. All right, so let's find out first. We have 500 milligrams has been prescribed, and the drug concentration is 10 milliliters is the same as 125 milligrams. So this calculation tells me how many milliliters of the solution we're going to need to use. We canceled milligrams, that gives milliliters. 125 will cancel into 500 4 times. So we end up with 4 times 10, 40 milliliters. All right, so once that is mixed together, pour the 40 milliliters in with the 400 milliliters. So now the flow rate is going to be 440 milliliters in 8 hours. Not 400, but 440 milliliters in 8 hours. Now, we want to know the flow rate in drops per minute, so now we're going to bring in the drop factor. And I want drops on top, so I'll put 12 drops over 1 milliliter. 12 drops over 1 milliliter. And milliliters cancels, giving drops per hour. And then we got to replace hours with minutes. So I'll put 1 hour over 60 minutes. And that gives us our drops per minute, which is what we wanted to end with. So I want to finish with drops per minute, and indeed that's what we have. So let's write the numbers out here. I've got 440 times 12 over 8 times 60. And I don't think this is too bad. 12 divides into 60 5 times. And 8 goes into 440. I believe that goes 55 times. Yes. That goes 55 times. So I end up with 55 over 5, which is 11 drops per minute. So there's our flow rate we wanted, 11 drops per minute. Okay, so I wouldn't rush these problems. Read through them carefully, think ahead. Well, what I would say, try to visualize what you need to do. You know, if you were handling this problem, what would you be doing? You would first have to mix the drug solution together so you have the right amount of liquid. It gets poured into the IV, and then we have more liquid than the original 400, and so we go from there. So anyway, again, I would try to think ahead on these problems, plan ahead, maybe try to visualize what you would be doing, and I think that will help you figure out the how to solve or at least how to tackle these problems. This problem is begins with a lot of information that we have to piece together, and it also includes the patient's body weight in the calculation. So let's get started. The order calls for 500 milliliters of D5W containing 120 milligrams of a drug. The patient weighs 116 pounds, and the order is for 0.012 milligrams per kilogram per minute. And what is the flow rate in milliliters per hour? All right, well, you might want to pause this and think about, you know, how would you begin to solve this problem? What are you looking for? Where would you begin? And see if you can crack it on your own. I would begin with the patient's weight. Patient weighs 116 pounds. So, put that down. And I'm going to circle or underline here the information as I use it. Okay, well, we have kilograms appearing, so we're going to need to convert pounds into kilograms. So 1 kilogram is 2.2 pounds. And then that cancels the pound units, leaving kilograms. Now let's bring in the unit with kilograms. And this is that new one we spoke about. 0.012 milligrams per kilogram per minute. So milligrams per kilogram per minute means I'm going to divide by both kilograms and minute. And we see that cancels off the kilogram units. So now I'm down to milligrams per minute. And what do we want? We want milliliters per hour. All right, well, I'm going to have to replace milligrams with milliliters. And how should we do that? This is where the drug concentration comes into play, because up here we have 500 milliliters contains 120 milligrams of this drug. So let's put milligrams down below, 120 milligrams. On top we have 500 milliliters. And so that canceled off the milligram units. I have milligrams per minute and I want milligrams per hour, so I just have to bring in the hour units. 60 minutes over 1 hour. And that cancels off minutes. So we have the correct units, milliliters per hour. Now it turned out here we used all the information that was given to us, and that's not always true. Sometimes these problems give you a little more information than you really have to solve the problem, so you have to be careful about that. Keep an eye out for that. Alright, so we have kind of a long calculation here. Let's see what we got. We have 116 times 0.012 times 500 times 60 over 2.2 times 120. And there are only about 1,000 ways to do this problem. Well, where shall we begin? I'm going to start by getting rid of decimals. So you may not like the way I do my arithmetic, and that's okay. I think a lot of people are very comfortable with just doing some obvious cancellation and then just multiplying and dividing. That's okay. I'm gonna show you some of my tricks, and if you don't like it, that's okay. Do it your way. Just do it accurately. But here's what I like to do. If I made this one 500 a 1,000, I'm making it twice as large, which means I need to make this number half as large. So I'm going to borrow a factor of 2 here and make that 1,000 and cut that down to 30. Now the reason I did that is because 1,000 times this number gives me 12. No decimal. So that was an easy way to eliminate this decimal. This gives me 116 times 12. And I also have the 30, which, well, let me keep the 30 up there. Because down here I'm also going to get rid of my decimal by borrowing. So if I borrow a 10 here and multiply there, I get 22 times 12. So I end up with 22 times 12. So this was a way of canceling off decimals. And then we see that the 12s cancel very nicely here. And we can also cancel off a 2 with the 22, make that 11, and make this half of 116 is 58. So I'd rather not divide 2 into 30 because 30 is easy to multiply with. It's easier to multiply with than by 15. So I have 30 times 58 over 11. So I'm going to have to make room here to finish. We wanted milliliters per hour, and I do have those units, milliliters per hour. So we are safe in that regard. We just have to finish the calculation. Alright, so I got, let me rewrite it, 58 times 30 over 11, and it's milliliters per hour. Alright, so may as well go 30 times 58. 30 times 58 will be 15, 17, 1,740, I believe. Okay, over 11. So divide 11 into 1,740. I'm going to make some room down below here. So I'll cross off some of this stuff. Alright, so we're dividing 11 into 1,740. And goes one time. Bring down a 6. 5 times 11 is 55. That's 9, 0, 8, 88. And the next decimal is going to be a 1. So let's round it off to 158 milliliters per hour. There we are. So there's the flow rate on this problem. A lot of arithmetic there. But possibly the more important thing is make sure you get it set up correctly, understand how that's set up. I realize that when you get to the real world, you can look for a calculator and punch all those numbers in. Okay, so let's go on to another problem. This problem introduces yet another new issue for us, which is calculating the duration or the amount of time it takes for an IV solution. So let's read through it. An IV infusion, 500 milliliters, began at 8:30 a.m. The flow rate is 21 drops per minute, and the drop factor is 15 drops per milliliter. When will this infusion end? All right, so we want to end up with what? We want to know the amount of time it takes for this IV to empty. So we're going to basically turn the 500 milliliters into time. We began with 500 milliliters, and I want to know how long it takes to empty. So when I finish with this problem, I want to finish with time in my numerator, either minutes or hours in the numerator. And so now before this, you've always seen time appear in the denominator because it's part of a flow rate in terms of drops per minute or milliliters per hour. But here, if we want to end up with time, time has to be by itself, has to be a numerator. You know, it makes no sense to end up with 1 over minutes or 1 over hours as your unit. Now, that unit does actually make sense in some parts of physics when you're dealing with frequencies, but that's that's totally unrelated to what we're doing here, and so it only makes sense to end up with time in the numerator. All right, so but I started with the amount 500 milliliters because that's being used to that's being drained, so we're going to use that to calculate time. By the way, let me mention, never use time a day in a drug calculation. Okay. You simply can't feed 8:30 into this problem. It's just never going to work. Now, we will use it at the end of the problem. Once we know how long the IV takes to drain, then we can add that amount of time to 8:30 and answer the question of the problem. All right, but first of all, let's find out how long it takes. 500 milliliters. And what up here contains milliliters? Well, my drop factor has 15 drops per milliliter. So I'm going to use that next. And I want to cancel milliliters. So I have 15 drops per milliliter. That canceled off milliliters because when you look at this information, how am I going to turn milliliters into minute? Well, I have to, for starters, I have to get rid of milliliters. And the only way to get rid of milliliters is to use the units which contain milliliters. So I've replaced milliliters with drops, but now my next problem is how do I cancel off the drops and replace with time? And that's where our flow rate comes into play, 21 drops per minute. And so it takes, we need to invert that because we want to cancel drops here. So 21 drops will go in the denominator and 1 minute goes in the numerator. So you see that the drops cancel and I have what I wanted. I have a time unit, minutes. And we could decide if we want to turn that to hours or not. I'm kind of inclined to just go ahead and calculate the minutes, and then we'll worry about hours from there. And so that will probably avoid unnecessary fractions or decimals. And I think we're going to end up with some fractions here anyway. Well, let's write out the numbers before we do anything. So I have 500 times 15 over 21, this is minutes. And we can do a little simplifying here. I'll divide 3 into 15 and 3 into 21. So I have 5 over 7. So let's see, 5 times 500 is 2,500 over 7. And let's see, how will 7 go in the 2,500? I'm going to make a little room upstairs here so that we don't get too cramped on the board. I would recommend, don't cramp your work when you do it, when you do your arithmetic. All right, so I have to divide 7 into 2,500. And it goes 3 times here. And that goes 5 times. And that goes 7 times. Leaves a remainder of 1, so my next decimal is going to be a 0.1. So this would round off to 357 minutes. So let's write that. 357 minutes. Okay. Now I just happen to recognize that 350 minutes, 7 minutes, is 3 minutes short of what? 6 hours. So, or you could say, well, this is 5 hours and 57 minutes. So this is 5 hours, 57 minutes. How do you know that? Well, you know, convert 357 minutes to hours. Some of you may be a little more comfortable with this calculation here. I need to convert 1 hour is 60 minutes. And so that gives me a fraction, 357 over 60. Well, when you divide 60 into there, it goes 5 times with a remainder of 57. Well, the remainder of 57 is 57 minutes. So 5 hours, 57 minutes. Okay, so let me see. This is going to get... infusion ends... What? The infusion ends... Oops, I spelled that right. Ends at... Okay, now it started at 8:30 a.m. So if I add 5 hours to 8:30, actually if I add 6 hours, let's go with 6 hours. So 8 o'clock, 8:30, all right, so that's 9:30, 10:30, 11:30, 12:30, 1:30, 2:30. So 6 hours is 2:30 p.m. 3 minutes less will be 2:27 p.m. 2:27 p.m. All right. Now I don't know if you can get by with just calling it 2:30 p.m. or not. I'm not in this field, but yeah, a little more accurate would be 2:27 p.m. So there we go. I have a little side topic in my book, which I thought is a good idea to cover in the videos as well. There's some misconception sometimes in converting minutes to hours. So let's look at this example. Convert 255 minutes to hours and minutes. All right, now if you have 255 minutes and convert to hours, so I have 1 hour is 60 minutes. Well, a lot of you would know probably in your head to divide by 60 anyway. And since after we get done with you here at the college, you'll be able to use calculators finally on this stuff when you're in the real world. It would be just tempting to just punch this in your calculator. All right, so what does your calculator show? Or if you do this manually, what you're going to come up with is 4.25 hours. Okay, so here's my point. Here's the crux of the matter. That is not 4 hours and 25 minutes. Okay, that's the misconception. The 0.25 is a decimal, and decimals are based on parts of 100. Minutes, however, are based upon parts of an hour, and there's 60 parts in an hour. So when we go to minutes from hours, we're using a different kind of counting system than our ordinary decimal system. So that's certainly not 4 hours and 25 minutes. If you think about this, this is actually 1/4 of an hour, 4 1/4 hours, which would be 4 hours and 15 minutes, because I think everybody has in their head a quarter hour is 15 minutes. So just to justify it, 0.25 of an hour, if you change that to minutes, then multiply this out, you will get 15 minutes. So be very careful about that, that misconception. The decimal on hours does not translate exactly as it says into minutes. Not the same thing. You have to convert the decimal to minutes. So this is 4 hours and 15 minutes. Now, personally, I would look at 255 over 60 as 4 and 15 sixtieths, which is 4 hours and 15 minutes. You know, if you reduce the fraction, it's 4 1/4. 4 1/4 hours is obviously going to be 4 hours and 15 minutes, not 4 hours and 25 minutes. So anyway, I like to make a big deal of this because people do fall into this trap. I see this quite often in this course and also in other classes whenever time comes up like this. This problem is probably going to be one of the trickiest ones you'll see in this course, and for reasons I'll explain here in a minute. But let's read through it. The order calls for 60 milliliters of a liquid drug to be added to 500 milliliters of D5W, total of 560 milliliters. The patient weighs 80 kilograms, and the patient is to receive 0.3 milliliters per kilogram per hour of the drug. The drop factor is 10 drops equals 1 milliliter. Find the flow rate in drops per minute. All right, now it's probably not apparent why this could be tricky, but here it is. It's the fact that we're mixing a liquid drug with another liquid. We're mixing milliliters with milliliters. And so we'll see that in a minute, because we need to use the drug concentration in this problem to do it properly. And you could, if you're careless, a little bit careless in interpreting this, you could on the surface get the correct units and yet be way off, under-medicate the patient. So here we've got to be a little more careful with units than normal, because the crux of it is that there's a distinction between these milliliters, which is pure drug, versus these milliliters, which is D5W. And so we have to make that distinction. All right, so let's begin as we always do with the patient information. Patient weighs 80 kilograms. So I'll write that in. 80 kilograms. And there's a compound unit here which uses kilograms, and that's the 0.3 milliliters per kilogram per hour of the drug. All right, now I'm going to write this differently than we're accustomed to. All right, now 0.3 milliliters is more than just milliliters here. I want to call that 0. milliliters of the drug. So let me write in the word drug. And this is per kilogram per hour, right? Per hour. Okay, so this cancels kilogram. So the reason I wrote drug there is because the drug is not what is going through the IV tubing. It is a mix of the drug with the 500 milliliters of D5W. So the total liquid amount, 560, is what's flowing through, not just the pure drug. And so we have to calculate, ultimately, the flow rate in terms of the total mix of liquid, not just the drug amount. So that's why I wrote that in here, because next I want to convert this amount of drug to amount of liquid, and we need to factor in the drug concentration. So the concentration, we have 60 milliliters of the drug contained within 560 milliliters of liquid. I think I'm going to have to make my parentheses a little larger here. Liquid. and these cancel. Not only does the word drug cancel, but the milliliters cancel. So now that's very important, because if I didn't distinguish between drug and liquid, we could have left this off and we would have milliliters, and we could have ended up with the proper, what would appear to be the proper units in the problem, which is drops per minute. We could get drops per minute without using this drug concentration. But it would be a fallacy, because we would be calculating it based upon pure drug rather than the amount of total liquid. And so that would end up actually under-medicating your patient, which can in some cases be every bit as much dangerous as overdosing or over-medicating. So I want to make a big deal of this, because it's such an important idea here to distinguish between the milliliters of drug and milliliters of the liquid. Very important to consider that here. Otherwise, patient may be in trouble. Now, to finish the problem, we need to bring in the drop factor and also turn hours into minutes. So I'll try to fit all this in my board here. Drop factor, 10 drops per milliliter. So uncancel milliliters. So that's 10 drops per milliliter. And this is milliliters of liquid, because what's going through the IV tube is milliliters of liquid. So this is the proper amount, or proper units, milliliters of liquid, canceling off. I have drops per hour. I need minutes, so I'm going to put 1 hour up here and 60 minutes down below. And I managed to fit this on the board. So I do have drops per minute. So there's our complete calculation there. Just one more time, I can't emphasize this too much, to be very, very careful when you're mixing the liquid drug with some other kind of liquid, that you're not mixing up your units, milliliter units there. Okay, very, very easy to do if you're not paying much attention. All right, so let's see. I'm going to write these out. This is 80 times 0.3 times 560 times 10 over 60 times 60, and it's drops per minute. So now we have a lot of arithmetic. Okay, so how about we do this? I'm going to multiply 10 times 0.3 to get 3. So I'm just going to rewrite it here so it's a little clearer in the video. 80 times 3 times 560 over 60 times 60. Now let's think about doing some other reduction here. I'm going to cancel off a power of 10 by crossing off those zeros. I'll cross off these zeros there. And let's see, I'm going to race up here so we can finish up clearly. You know, it doesn't matter what order you do your calculations in, as long as your arithmetic is accurate. So you don't have to do things exactly the way I do it, but I'm just showing you the way I think through this arithmetic. All right, let me see. We have 8 times 3 is 24 times 56. And I really don't want to multiply those if I can help it. It's over 6 times 6. So let's see, we can cancel 6 into 24 4 times. That's great. I could cancel a 4 into each of, actually I can cancel 4 into 6. Becomes a 2 over a 3. So I have 2 times 56 over 3. Now 2 times 56 is 112 over 3. So what would that be? Well, let's just go ahead and do it. So 3 goes into 11. How many times? Goes 3 times. 9. 7. 37.3 drops per minute. And I think you would round that off always to whole numbers. So let's call that 37 drops per minute. There we go. So I'm going to cheat here a minute and see what our answer would have been by using a calculator, and see what our answer would have been if we had not used this factor here, this drug concentration factor. So let's see, 37.353 times 560 divided by 60. Oops, I had that backwards. Alright, so I would have been dividing by 60, multiplying by. Try that one more time. Times 60 divided by 560. We would have gotten actually four drops per minute if we hadn't factored in the drug concentration. This poor patient would have only gotten 4 drops every minute instead of 37 drops per minute. So you can see that he would have been getting roughly 9 times less than what he was supposed to be getting. So anyway, there we go. That's I would pay a lot of attention to the issue in this problem, and because it's a good one. Well, we can't leave this chapter without using body surface area, and this is a pretty good problem with a lot of stuff in it. The order calls for 0.045 milligrams per square meter per minute of a drug, which is to be added to 400 milliliters of D5 and 0.45 natural saline and infused over 5 hours. The patient's body surface area is 2.06 square meters. The drug label reads 1.5 milligrams equals to 5 milliliters. What will be the flow rate in milliliters per hour? All right, well, it's not quite as simple as just saying the patient's going to get 400 milliliters in 5 hours, because we have to first mix up the drug solution, pour it into the IV, and then do the flow rate calculation. So really two big steps here. So first of all, I want to know, well, how much of the drug solution am I pouring into the 400 milliliters of this stuff here? All right. So as usual, let's begin with the patient information. The patient has a body surface area of 2.06 square meters, and the dosage rate is up here, which contains the square meters. So that's worded a little bit differently, but it's still 0.45 milligrams per square meters per minute. And so we have 0.045 milligrams over square meters times minutes. So that cancels the square meters, and we have milligrams per minute. Now, we're going to infuse this over 5 hours. And so I want to also know how many milliliters that have to be added to the drug bag. So let's see here. We have, so far we've used this information. We've used the patient's body surface area. We used the drug dosage. And let's use the concentration, drug concentration. So the concentration will allow us to turn the solid measurement, weight measure, milligrams into milliliters. So I have 5 milliliters over 1.5 milligrams. All right, so this gives us milliliters per minute, doesn't it? All right, well, again, I haven't factored in the other 400 yet. And so this gets a little crazy here. How I'm going to handle this is I want to know, well, how much drug, total drug solution, is a patient going to receive in 5 hours? So as this problem evolves in my mind, I'm seeing, well, okay, I have to know how much to pour into the IV bag. All that has to be dispensed in 5 hours. So I need to know how much of the drug solution will be poured in. That will last 5 hours. All right, well, I have to first change minutes to hours. So I'll put 60 minutes over 1 hour. And the whole thing takes 5 hours. So cancel my units here. And milliliters per hour, if I multiply by 5 hours, then I've canceled off the hour units, and I have milliliters. So I finally figured out how to get the total amount of drug solution that we need to pour in and add to the 400 milliliters. So here's our first calculation, and this is the bad one here. So let's go through and work this out. I have 2.06 times 0.045 times 5 times 60 times 5 over 1.5. Okay, well that's going to be fun. Let's see here. I'm probably going to have to make some room somewhere to work this out. The 1.5, see 15 goes into 60 4 times, so 1.5 goes into 60 40 times. So let's do that. So I'll cancel this, and that gives me a 40. And 5 times 40 is 200, and 5 times 200 is 1,000. So this calculation here, 5 times 40 times 5 gives me 1,000. So I have 2.06 times 0.045 times 1,000. Well, to me it's looking a lot better, because now if I multiply 1,000 times 0.045, I'm going to get, this becomes larger by 3 places, this becomes 45. So I end up with 2.06 times 45. All right, so let's work that through. I'm going to have to do a little racing here to make room. And let's see. All right, I got 2.06 times 45. It's a 1030 there. 24, 824 there. 0, 7, 2, 9. I have 2 decimal places, so it's 92.70 or 92.7 milliliters. Now, don't forget our units were milliliters. So let me write that conclusion out just for sake of notes here. We found out that the amount of drug solution that must be poured into the IV bag is 92.7 milliliters. So 92.7 milliliters of the drug solution is added to the 400 milliliters. There we go. So we have a total now of 492.7 milliliters of liquid. So there's your total liquid, and it's being infused in 5 hours. 5 hours. So we wanted milliliters per hour, so there's our calculation, milliliters per hour. And all right, so that's going to be just a little bit under 100, isn't it? I don't know if let me rewrite that a little more neatly. I think most people would just divide 5 into 4, 92.7, but I'm a little different, and so you know, dividing by 5 is a little bit like multiplying by 2. So if I multiply 2 times 492.7, I get 9854. Well, I know it's just a little bit under 100, so actually it's 98.54. is what how 5 goes into that number. So this would equal to a flow rate of let's see, 98.5 milliliters per hour. Let's call it 99 milliliters per hour. There we go. So I'm not sure you can set milliliters per hour in terms of decimals. It's possible some machines would allow for that. I just don't know. To me, it makes sense to call it 99 milliliters per hour. That's pretty close. So there we go. That problem had a lot of thinking to go along with it. So my advice in this chapter is read these problems and think about them, and try to imagine yourself doing the steps in setting this up. You know, as far as preparing the drug, in some cases mixing it with pouring into the IV bag, and then going from there. You know, looking at the tubing, taking into account the patient's weight, the drug concentrations. All those factors will show up in the statement of the problem. Try to visualize how you would be doing this, and I think you'll have a better chance of thinking through it correctly.